Viewers like you make this program possible. Support your local PBS station.
$252 million years ago, a catastrophe killed nearly all life on Earth.
This is the closest our planet has ever been to going back to square one.
As many as 90% of species across the Earth died.
This extinction was much greater than the one that ended the age of the dinosaurs.
But an asteroid wasn't to blame.
It is not easy to kill so many species, so this had to be something utterly catastrophic.
The culprit was lurking just beneath the surface.
We are finally able to piece together clues from this ancient crime scene.
Now we finally know the culprit. Enormous volcanic eruptions.
It is as if the Earth itself turned on life.
Yet some life stubbornly hung on. And when the threat passed, thrived again.
Mass extinction events, although terrible, provide new opportunities for life.
Death and extinction shape the biodiversity of the living world.
From the ashes of a lost world comes the story of ancient Earth. Inferno, right now on Nova. In a time long before the rise of human civilization. Before the last glacial period. Before an asteroid impact wiped out the dinosaurs. In fact, a time before dinosaurs even existed at all. An apocalypse destroyed nearly all life on Earth. And it may hold lessons for our future. Over 250 million years ago, the disaster looms. $253 million years ago. Earth looks very different than it does today. On one side, a water world, no land in sight. But on the other side, Earth's land masses are clustered into a colossal supercontinent. This is Pangaea. Lush forest ecosystems flourish. And its waters teem with weird and wonderful creatures. The Permian Earth is rich, diverse, and full of life. There are no ecosystems on Earth today that look exactly like those of the Permian period. But some share a few similarities.
life at the end of the Permian was beautiful.
We had a very diverse ecosystem, both in the marine realm, but also on land.
It doesn't contain any mammals, any birds, any flowers, so completely different.
But you would recognize some of the early forerunners to our modern conifers, for example.
So the rock I'm holding here has a lot of fossil leaves from a plant called Glossopterids, one of the tree-forming plants that lived in the southern hemisphere. It's pretty cool to hold a fossil from that time period. It's like going back in a time machine.
Pangaea is dominated by animals that lived before dinosaurs and mammals evolved. Forgotten creatures that scientists only know about from the fossil record.
You would have had these giant armored herbivores with these crazy big bony sort of processes on their skulls called parasaurs.
And the big predators are called gorgonopsians. They've got a mouthful of sharp teeth. Smaller sharp teeth up in the front, and then these incredible sabers. This is the first time that we know of predators evolving saber teeth to kill their prey.
On land, during the Permian, we had insects as well. We see wings, some of which span more than a foot long, much larger than the ones we see today.
And we also see the very first beetles. So beetles haven't appeared yet in the fossil record until about the Permian.
There is also great diversity to be found in the oceans.
The oceans would look completely different to now, but with a couple of familiar characters, ray-finned fish and sharks. There were lots of reefs, but made of very different types of organisms.
And there would have been trilobites scuttling about on the ocean floor, more or less seafloor bugs.
By the end of the Permian, life had become very rich and diverse in a whole range of habitats, both on land and in the sea.
I would love to go back and see all these animals living together. It would be a great prehistoric safari.
But life is about to change forever. Deep beneath northern Pangaea, superheated liquid rock, magma, is rising. It pushes up against the Earth's rigid upper layer, the crust, until it can take no more. The crust splits open. Within hours, the local landscape is torn apart. Cracks grow, forming great curtains of fire as lava floods onto the surface. The insides of Earth spew out.
The eruptions came from a giant volcanic system in northern Pangaea called the Siberian Traps.
The remnants, the rock record of these volcanic eruptions still exists in Siberia.
There's a huge footprint of lava left behind, covering a huge area of modern-day Siberia.
I've actually been to the Siberian Traps and floated down rivers where both sides of the river were huge cliffs of stacked up lava flows.
These rocks reveal that the Siberian Traps erupted on and off for around 2 million years, emitting about 700,000 cubic miles of magma and rock.
The eruptions at the end of the Permian are absolutely huge. They're vastly greater in scale than anything that we've seen today.
This is a planetary scale eruption that would cover the United States in lava around 300 yards deep.
We can try to grasp the scale of these eruptions by comparing them to recently active volcanoes.
Witnessing a volcanic eruption just gives you a sense of how powerful the Earth is.
The explosions make the ground throb, so you can feel sound traveling through your whole body. And the smell and the fumes can be really intense.
In 2021, the volcano Takogaiti erupted and released around 300 million cubic yards of material.
That's enough to fill 80 football stadiums?
Other eruptions in human history, like the Krakatoa volcano, were much bigger.
So when Krakatoa erupted in the 1880s, it spewed out about 2 cubic miles of magma.
The eruption was so large that it led to global temperature decrease because of the gases emitted.
But even Krakatoa was minuscule compared to the eruptions of the Siberian traps.
The Siberian traps would be like a Krakatoa erupting every year for 300,000 years.
Eruptions on this vast scale are devastating to life nearby. Fire fountains blast volcanic material up into the atmosphere. Untold numbers of creatures perish in the forest fires that burn close by. Sulfur dioxide builds up and reacts in the atmosphere, partially blocking out the sun. Plants wilt and die as a volcanic winter sets in. Ash falls on a dying landscape. After each eruption, vast swaths of northern Pangaea are scorched. But is it enough to cause mass extinction? Although these early eruptions are huge, Pangaea is big too. Most of the supercontinent remains untouched by deadly lava. Elsewhere in Pangaea, something curious is happening. A strange haze hangs in the air, created by nutrient-rich volcanic ash and sulfur. Blown here from the eruptions happening thousands of miles away. At first, plant life seems unaffected and may have even benefited from the nutrients in the ash. There is no mass extinction for now. But death is coming. These rocks, formed 252 million years ago, contain evidence of a massive die-off.
As we go up in this section, we are traveling forward in time. So these rocks here are older than the ones on the top.
These ancient rocks were formed on the ocean floor before being pushed up to make these mountains.
Rocks not only tell us about the environment in which they were formed, but something extraordinary about them, it's that they are full of fossils. So for example, clams, marine snails, shell organisms, and other fossils like these nautilus that were living during that time.
The diverse fossils in these rocks show that this was a vibrant marine ecosystem. But that was about to change.
So all the complex ecosystem that we're seeing here, full of life. After this level, it becomes like super hard to find fossils. And the things that we do find are really tiny. And we see how all the diversity that we have below seems to just disappear.
Over just a few hundred years, a geological blink of an eye, almost all life here vanishes. This is death on an astounding scale. But curiously, these rocks show no direct evidence of this volcanic activity.
So it's actually really surprising that here we are thousands of miles away from the eruptions going on in the north of Pangaea. And still you see the consequences going on there. This event, it's not only found here, but also across the planet. Life just vanished. You will see this line of that. You will see how life seems to just vanish.
How could volcanic eruptions in the north wipe out so much life across the entire planet?
Scientists think that the Siberian Traps was erupted in different phases. Phase 1 was characterized by lava flows for around 300,000 years.
It's not just Earth's surface that is affected by the eruptions. They also eject billions upon billions of tons of gas and tiny particles into the air. Water vapor, sulfur dioxide, toxic heavy metals, and carbon dioxide, which begin to disperse in the atmosphere.
So what we want to understand is, how were these gases affecting the planet?
Sulfur dioxide and carbon dioxide have opposite effects on the Earth's atmosphere. Sulfur dioxide reflects sunlight back into outer space, causing global cooling, whereas carbon dioxide is a greenhouse gas and can lead to global warming.
The cooling and heating effects of these gases in the atmosphere act on different timescales.
Sulfur dioxide tends to stay in the atmosphere for a shorter period of time because it can get rained out.
But carbon dioxide can stay in the Earth's atmosphere for hundreds, if not thousands of years.
After each pulse or surge of volcanic activity, any cooling effects from sulfur dioxide wouldn't last long. But for heat-trapping carbon dioxide, it's a different story.
Carbon dioxide released during one pulse of the Siberian Traps volcanism would have stuck around for the next pulse.
And as carbon dioxide builds up in the atmosphere, it affects the entire planet.
So the biggest driver of environmental change that leads to mass extinction is not the lavas themselves. It's the gases that they release into the atmosphere.
We're witnessing the impacts of increasing levels of greenhouse gases today, but at a much smaller scale.
As we're adding more carbon dioxide to the atmosphere today, the global temperature is rising, which lead to a series of environmental changes.
Studying our oceans and the impacts of modern climate change gives clues as to how life might have been affected by the warming 252 million years ago.
We can see right now in our own world coral reefs affected by climate change. The oceans are getting warmer and they're getting more acidic.
This is really stressful for corals, and it causes vast swaths of places like the Great Barrier Reef to bleach, turning corals white.
Bleached corals are more likely to die, and this can have devastating consequences.
Coral reefs are a poster child ecosystem for one that's complex and full of life. If you start taking away those corals, it's really easy to see how ecosystems like that can collapse.
But it's not just coral reefs that are being pushed off balance by present-day climate change.
As temperatures rise in the ocean, that allows algae to reproduce really quickly, and when it rains, that pushes nutrients that we have on land into the ocean, and the algae feed on that and grow, resulting in these enormous algal blooms.
These vast algal blooms today have consequences for life in the oceans. And in this case, it's not the rising temperatures that kill.
As algal blooms occur, they actually take up the oxygen in the ocean, leaving less oxygen behind, and therefore organisms can't live in it.
Changes in modern-day ecosystems show how the process of extinction can play out.
So these subtle changes may not seem so striking at first. The loss of one species here, the change in this environment over there. But given enough time and given enough of these subtle changes, you can have drastic negative impacts on ecosystems.
This slow, relentless change is likely what led to the huge loss of life at the end of the Permian.
Mass extinction can take place slowly, over thousands or even millions of years, as environmental changes become too much for many species to adapt to. In Pangaea, as greenhouse gases build up over hundreds of thousands of years, the temperature rises.
During the mass extinction, it is thought the oceans warmed up between 14 and 18 degrees Fahrenheit, and on land, they warmed up even more.
On the supercontinent, trees begin to die. Holes appear in the canopy, bathing the ground in sunlight. For some life, it's an opportunity. Weed-like lycophyte plants flourish in this new environment. And with the warmer temperatures, other species migrate. Woody, seed-bearing plants called cycads that are believed to have once grown in the tropics now thrive closer to the poles. Fossil evidence suggests that some ecosystems are now more diverse than before the warming began. But this ecosystem is still vulnerable. A few more degrees of warming, and it could crumble. But then, something strange happens. A silence descends on the Siberian traps. Greenhouse gas emissions, including carbon dioxide, taper off. After 300,000 years of lava flows, the eruptions finally stop. For now. When scientists try to calculate the amount of greenhouse gases released by the eruptions, and then compare that to the amount of global warming implied in the rock record, something doesn't add up.
When we add up all the carbon we think we would have got from the magmas, making our best guess, it's not enough to account for the level of climate devastation that the geological record suggests.
About half of the greenhouse gases needed to drive the extinction at the end of the Permian are missing.
So where do all the extra greenhouse gases come from? One answer can be found underground. It's quiet on the surface. But beneath the Siberian lava field, reaching almost 8 miles deep, hot magma still flows, forming great reservoirs underground, encountering rocks hundreds of millions of years old deep below.
The amount of lava that over time was released from the Siberian traps was so immense that it capped the Earth's surface eventually.
After 300,000 years of lava building up on Earth's surface, the path of the magma changes. The volcanism enters phase 2.
Instead of lavas flowing on the surface, magma started to spread laterally underground.
The Earth's crust is in some ways like a layer cake. So as the magma forced its way up, it encountered different layers of rock.
One such rock was coal.
In this case, the magma literally started burning fossil fuels, similar to the way we're burning them through our pistons and power plants.
But carbon dioxide doesn't act alone. It isn't just coal in the Earth's crust.
Beneath the volcanic rocks released by the Siberian Traps eruptions lies an ancient seabed that contains the salt left behind whenever the sea dried up.
In some places, the salt layers were 650 feet thick. Now that's quite a lot of salt.
When salt and magma make contact, the consequences can be devastating.
So salt is, I have a piece with me here. On its own, salt's a fairly sort of innocuous, not very dangerous looking rock type. As we know, we put salt on our food and so on, but it can be very dangerous.
So when the hot magma comes into contact with these salt layers, it bakes them, releasing all sorts of horrible gases.
The burning coal and the heated up deposits of salt that were triggered by these eruptions just basically created a huge time bomb.
The salt and coal underground are heated to as much as 1,400 degrees Fahrenheit and begin to release their toxins. The pressure beneath the surface increases until the land above can take no more. Volcanic material flies miles into the air. Each eruption releases more greenhouse gases from burning coal. This is thought to be the missing link that accounts for the full extent of global temperature rise. And the scorching salt releases deadly chemicals too. Toxic gases called halogens, which can spell trouble if they reach the ozone layer.
It's a layer high in our atmosphere, and what it does is it protects our planet from ultraviolet radiation from the sun, which is very harmful for all life.
When these halogens react with the ozone layer, they weaken it, and that allows harmful radiation from the sun to come through.
We've seen the Earth's ozone layer temporarily degraded in recent history. In the 1980s, industrial activity created a hole in the ozone layer over Antarctica, one that is now closing. But during the extinction event at the end of the Permian, the halogens damaged the ozone layer on a devastating scale, bathing life with a massive dose of harmful ultraviolet radiation. The loss of ozone is thought to have contributed to the extinctions. But can scientists find a way to prove it?
A way we can really understand the mass extinction is by looking at fossilized pollen grains, microscopic reproductive structures plants left behind in the fossil record.
Some tree pollen has remained relatively unchanged for hundreds of millions of years. So modern-day pollen should look the same as that in the fossil record.
So I have a picture here of a modern pollen grain of a pine tree. It's basically one central body, and there are these two structures on the side that are called sacci. These help this grain catch the wind and fly. And this is very much what the pollen grains in the end Permian trees would have looked like under normal conditions.
But the fossil pollen from the extinction event doesn't look the same.
So during the mass extinction at the end of the Permian, the pollen grains started looking more like this. And boy, they're strange. This one here has 3 sacci when it should have 2. And this one has 4 sacci. This here is 2 grains that are stuck together. They come in all sorts of strange shapes and forms that really deviate from what a healthy pollen grain should look like. They're malformations.
Could increased ultraviolet radiation be the cause? To find out, paleobotanist Jeffrey Benka grew modern pine trees under high ultraviolet radiation in a lab.
We wondered if the plants would just die on us under these extreme conditions, but that's not what we found. Instead, we found the exact same types of malformations in the fossil record were produced by our modern pines.
Although this high ultraviolet radiation didn't kill the plants outright, malformations in the pollen did have catastrophic consequences.
The results of this experiment are telling us that at the end of the Permian, the forests would have been sterilized, unable to reproduce.
It is a slow march to extinction. The Permian forests have been exposed to extreme ultraviolet radiation. Healthy-looking trees are now sterile. As trees die and are not replaced, animals lose precious habitat and food supplies dwindle. During the mass extinction, life on land is under threat from all sides.
The mass extinction at the end of the Permian is like murder on the Orient Express. There's not one killer that can do it all.
There's still a lot of debate about how all these killers came together to kill off life on land. We're talking global warming, heavy metal poisoning, acid rain, wildfires, deadly UV radiation. This was hell on Earth.
There probably were pulses of ozone weakening that were happening throughout the duration of the Siberian Trap's activity. But over even longer time spans, global warming was kicking in and really driving ecosystems to full collapse.
The collapse of life in the oceans is even more dramatic. The warmer, nutrient-rich waters contain less oxygen. Oxygen that marine life uses to breathe. And as carbon dioxide reacts with seawater, the oceans become more acidic. Algae and bacteria bloom across the planet, poisoning the oceans with the hydrogen sulfide they release. Creatures across the oceans die. Huge stretches of the seafloor become fetid beds of death.
So in the oceans, the combination of increases in temperature, loss of oxygen, and acidification all contributed to the loss of life we see at the end of the Permian.
These ocean killers could have worked together to be exceptionally devastating to ocean life.
Exactly how much life died is debated by scientists, because the fossil record is incomplete. But evidence shows that the great Glossopterus forests, the giant saber-toothed predators, and almost all marine life disappears. By the time the eruptions finally stop, the average global atmospheric temperature has risen as much as 22 degrees Fahrenheit. Countless species have gone. The rich complexity of life on Earth has vanished.
The words mass extinction are not lightly put together by scientists. They carry real weight, and the extinction at the end of the Permian was the most severe of all of these.
It's been called the mother of mass extinctions. It's been called the Great Dying. It's by far the worst thing that life has ever had to endure.
With so much death and destruction, how could any life hold on at all?
Life on Earth is adapted to living on Earth. It has evolved that way. And if circumstances change, organisms can adapt to that change.
And those that cannot adapt will eventually go extinct.
If species can adapt to the new conditions, it gives them an opportunity to thrive.
Death and extinction shape the evolution of life. It's through this act of creative destruction where one species go extinct that allows for another species to actually rise.
Over time, the combination of these interactions of extinction, adaptation, and evolution create resilient ecosystems.
But even resilient ecosystems aren't indestructible.
An ecosystem is a lot like a Jenga tower, where each brick is its own species. And as you remove 1 to 2 species, the ecosystem stays relatively intact. But the more species you lose, the more unstable the ecosystem becomes until it fully collapses.
Today, organisms are really struggling to adapt to an ever-changing planet.
And it's not just climate change, it's also things like habitat destruction,
loss of coral reefs, loss of sea ice, deforestation, loss of wetlands, loss of grasslands and prairies.
But even after ecosystems collapse, like they did 252 million years ago, some life survives. If it can adapt, there's a chance to rebuild. The Permian apocalypse isn't just the end of one world. It's the beginning of a new one. Fossil evidence is patchy, so scientists don't know exactly where life holds on. On land, some life likely survived near the cooler poles, and many creatures could have sought refuge underground, sheltering from blistering temperatures and intense solar radiation. And some life survives above ground too. A single type of plant dominates much of the post-extinction landscape. Pleuromaea, a hardy plant that makes it through the apocalypse. This ecosystem provides just enough sustenance for the cockroaches, who also make it through. Life endures. But the searing heat does too.
The period immediately after the Permian is the Triassic period, and it was very, very hot.
Scientists know about these conditions from studying fossils and the chemical composition of rocks formed at the time.
It's incredible what we can get from rocks. They look so unassuming, but actually they hold so many clues to past environments and past life.
We, for instance, know that there were forests growing on the South Pole. And to make that happen, you need a warm planet.
Temperatures on land would be 120 degrees Fahrenheit, possibly up to 140, with heat waves on top of that.
And that is so hot that in several places of the world, complex life would not have been possible anymore.
It's also hot in the oceans.
Surface ocean temperature may have reached as high as 100 degrees Fahrenheit, and that's as hot as a hot tub.
These extreme ocean temperatures would have been inhospitable to most ocean life.
The mass extinction at the end of the Permian was so devastating to coral reefs that for about 14 million years into the Triassic, we don't see corals anywhere on the planet.
For life to bounce back, the planet needs to cool down. Normally, over vast timescales, Earth's temperature naturally resets itself. Carbon dioxide is removed from the atmosphere, in part by reacting with rainwater. But vast areas of central Pangaea are desert. Little rain falls. It takes millions of years for Earth to cool. Much of the supercontinent remains barren and dry. But 18 million years after the mass extinction began, life is about to get an enormous boost. And traces of what that was can still be seen today. These mountains are largely made of a hard rock called dolomite. But hidden within them are layers of an altogether different rock. One that holds clues to an extraordinary time in Earth's history.
This is the rock that formed during this strange period of time. This is a sandstone. It's a relatively soft stone, and you can see all the single grains of the sand. And if you take this one in here, this is a softer stone still, and it easily breaks down in my fingers because it's a mudstone. These rocks in here are looking completely different from the ones below and above us, because these are sandstones and mudstones, whereas those above and below are dolomites.
The secret of this unusual layer of rock is how it was formed.
Sandstones and mudstones are sediments that are typically formed by the erosion of sand and mud on the continents which were washed into the ocean.
All over the Dolomites, there are examples of this strange layer of softer rocks made from sand and mud.
So now, of course, we have to ask ourselves, what caused this dramatic change?
The answer came from the sky.
And it was rain, a lot of rain. This episode lasted for a long time, about 2 million years.
A deluge on this scale seems so unlikely that when scientists first discovered the evidence, some believed it was just a local event.
But later on, evidence of it popped up also in China, Iran, North America. So nowadays, it is believed to be a global event. This period of time is called the Carnian Pluvial Episode.
"18 million years after the mass extinction began, the skies become heavy with moisture until the clouds burst. Rain falls across Pangaea, and Earth is changed once more. Lush forests grow again. This 2 million year event lasted just as long as the volcanism that preceded it, and may have marked the rise of a new life form.
The Carnian Pluvial Episode set the stage for the dawn of the Age of Dinosaurs.
My research suggests that this era of warm, wet conditions really boosted plant diversity. And from the plants, we get more herbivores and more carnivores, and dinosaurs are part of that growth. So this is Herrerasaurus. This is one of the first dinosaurs to appear just after the Carnian Pluvial Episode. And as you can see by the sharp teeth here, this was a meat eater, one of the top predators.
The Carnian Pluvial Episode and what it might have meant for dinosaurs is a brand new avenue of research.
We see a lot of fossils that we can't quite figure out exactly how they fit into the grand family tree of ancient life. And so we are working with some very difficult fossils, and putting all this stuff together is very, very difficult for scientists.
We can see that the ecosystems were changing. We can see that the climate was changing. But how those interact, what actually would have affected the dinosaurs, what would have caused them to be successful, we don't know yet. This is why there's so many paleontologists doing active research.
What scientists do know today is that the world of the dinosaurs will persist for over 160 million years. Life on our planet has been punctuated by catastrophes. And although the extinction at the end of the Permian might seem like a distant nightmare, it holds lessons for our own future.
Both the end of the Permian and today, we are seeing rising global temperatures, lower oxygen levels in the sea, and ocean acidification.
Today, there's no volcano. It's just us.
While we're not releasing as much greenhouse gas as was released during the entirety of the Siberian Traps eruptions, the fact is we're releasing them a lot faster today.
And our fast-changing environment is affecting life everywhere.
We are driving things to extinction at an extremely rapid rate.
If the loss of life continues to go unchecked, we may very well be in the midst of another mass extinction on this planet.
But even after the worst catastrophes in Earth's history, life recovers.
The extinction at the end of the Permian both shows us the fragility of life, but also shows us how resilient life can be.
The most amazing thing about life is how it bounces back from these devastating events. However, it comes back differently.
It takes a long time for life to rebound from these sorts of events.
If we continue on our current path, we risk altering life as we know it. We also risk our place as humans on this planet.
And yet, hope remains.
Human beings are an ingenious species.
We've gone from hunter-gatherers to traveling through space. If we could do all that, I'm confident we can sort out our current problems.
What does the legacy of mass extinction mean for our future?
Whether it's a massive eruption of lava or human beings burning fossil fuels, the Earth is going to be fine. It's the species that are living on the Earth at the time that might not make it through.
In the long term, the Earth will come back from where we are today. The question is just whether we as a species will be here to see it.
Be more PBS.